Hey guys, and welcome back to another video. In this video, we'll be talking about 2.5 logarithmic functions. Alright, so let's get right into it. Okay, so to begin with, the general form of a logarithmic equation is a log base b of x. Okay, and where a, where x cannot equal 0, where x is greater than 0, b is greater than 0, and b cannot equal 1. Okay? So essentially what a logarithmic function is, it is the inverse of exponential functions. Okay, so for example, if you had let's say log base b of x, right, and y equals log base b of x, you could just convert this to exponential. So the base is b, right? So you're going to have the base b, and then you're going to raise it to the y power is equal to x, right? So that's essentially how you convert back and forth between the two. But like I was saying, logs and exponentials are just inverses of each other. So let's say we have two functions, f of x equals log base b of x, and g of x equals b to the x. Okay, and so suppose we have a point s comma t on the graph of g of x, right? So by the definition of inverse functions, you switch input output, right? So that means that if s comma t is on the graph of g of x, that means that t comma s has to be a point on the graph of f of x. Okay, because remember, you're switching input output. And then another thing to notice is recall that inverse functions are just reflections of each other over the line y equals x, right? So if we had some function like this, assuming that it's exponential growth, this would be g of x equals b to the x. That would be the exponential. And then let's say we had the line y equals x like that. And so if you reflect this over the line, you should get the graph of log base b of x. So you get something that looks like this. Okay, and indeed this is the general form, the general shape of a logarithmic graph. Okay, and then another thing to notice is that we have a vertical asymptote. So for the logarithmic graph, we have a vertical asymptote at x equals 0, and which means, and it never crosses the x-axis, right? So the domain is also 0 not included to infinity, right? That's the domain for f of x. And then for g of x, the domain is all real numbers, but the range is restricted. So the range of this one is also 0 to infinity. So that's again just going back to how the domain and range for f of x for inverse function are the same, or the domain of f of x is the same as the range of g of x. Okay. All right, good. So now let's go back more in depth into how to convert between logarithmic and exponentials. So generally speaking, let's say we have some logarithmic on y equals log base b of x, right? So what this means exponentially is you have log base b, right? So that means that b is like the base to which you're raising the power to. And logarithms output the exponent, because in exponentials, the input is the exponent, meaning that logarithms, the output is the exponent, because input output is switched. So for the b, the exponent is just y, because that's what this is outputting. And then the input for logarithms is whatever the exponential's output. So the output for this is just x. So these two are equivalent statements, right? That's how you convert between logarithms and exponentials. All right, so now let's do some examples. So let's say we had log base 2 of 8 is equal to 3, and you want to convert this to exponentials. How do you do it? So first, what is our base? So it's log base 2, right? So our base is 2, and we're raising it to the third power, so we have 2 cubed, that's equal to 8. Okay? All right, let's do another one. Let's say we had log base 9 of 3 is equal to 1/2. So you have log base 9, so our base is 9, we're raising it to the 1/2 power, and that's equal to 3. Okay, so now let's do the other way around. So now let's say we had 2 to the 4th equals 16. So now convert this to a logarithm. So you have log, and then our base is 2. So you have log base 2 of whatever's outputted, because that's what you're inputting into the log. And then logarithms output the exponent, which is 4. Okay? And then part D, we'll do, let's say 3 to the negative 2 is equal to 1/9. Okay? So again, you have log, our base is 3, and of 1/9, because that's what the exponential is outputting, and that's equal to negative 2. Okay? So that's just some examples of how to convert from log to exponential, and then from exponential to log. Okay, good. So now let's talk about some common types of logarithms. So there's two main types of logarithms that you need to know. So the first one is the common log, and that's just log base 10. And then you have natural log, and that's log base e. And the shorthands for these are, so for a common log, log base 10, that's just like log of x. So if you have like log without any base, it's assumed to be log base 10, right? So that's like the default. And then log base e, we abbreviate that as just ln x, so natural log x. Okay? All right, good. So now let's do some examples with these. So suppose you had log of 415. What is this equal to? So for these ones, you would have to use a calculator to do them. So go ahead and pause the video real quick and see if you can find the values of this by using a calculator. Okay, so you should have gotten approximately 2.618. All right. Now go ahead and put this into your calculator and see what you get. All right. So now you had natural log of 415, and if you put that into your calculator, you should get approximately 6.028. Okay. So now is a very interesting and important property of logs, and this applies to all logarithms. If you have log base anything of 1, it's always going to be equal to 0, right? So this is actually a really good note. So note, if you have log base b, so base anything of 1, it's always going to equal 0, right? No matter what the base is. And this is because this is the same thing as saying b to the 0th power is equal to 1, right? So this is a known, we already know this, right? Anything to the 0th power is equal to 1. So this is basically just saying the same thing in logarithmic notation. All right. Okay. And then some more. Let's say we had log of 0, and let's say we had log of negative 2. So what would this equal? Well, remember, the domain of logarithms, x has to be strictly greater than 0. Okay, so 0 is not part of the domain, so this is actually just undefined. And similarly, negative 2 is not in the domain, so this is also undefined. All right, good. So now let's talk about the properties of logs and logarithms a little bit more in depth. So let's talk about their graphs specifically. So let's say we had exponential on this side, and I'll do log on this side. And let's just make like a table. Okay, so start off, the general equation for exponential is b to the x, and for log, it's log base b of x. Okay, intercepts, so next, so this is the general equation. Let's say equation. Okay, and then any like intercepts, so x and y intercepts. So exponential, you have a y-intercept, at 0, 1. This is for like the parent functions. And then for log, you have an x-intercept that's 1, 0. And this is going back to the same idea where if 0, 1 is on the graph of exponential, then if you switch it, 1, 0 has to be on the graph of log, right? And then domain and range. So the domain of exponentials is all real numbers, right? Negative infinity to infinity. And the range is 0, not included to infinity. And again, this is for the parent function. And so then log, domain, and range is switched. So the range of an exponential is the domain for log, so 0 to infinity. And then domain for exponential is the range for log, so negative infinity to infinity. Okay? And then asymptotes, I'll just abbreviate it as ASY. So exponential, the parent function has an asymptote, horizontal asymptote y equals 0. So horizontal asymptote. And then here you have a vertical asymptote for logs at x equals 0. Okay? And then the general graph, we can sketch it once again. So for exponential functions, it looks something like this, right? And there's 3 key points. So right here you have the intercepts, that's 0, 1. Then like somewhere over here you have 1 comma b, so b is like the base. And then somewhere over here you have negative 1, 1 over b. Okay? And then for logs, remember this is a reflection over y equals x. So it looks something like this. And let me actually draw on the asymptote. So you have a y equals 0 right here. You have x equals 0 right here. Okay. And again, right here is your x-intercept, so 1, 0. And then somewhere over here you have the point b comma 1. And then somewhere down here you have the point negative b, negative 1 over b. Here, negative 1 over b comma negative. Okay. So take a second and, get all that soaked in. And again, notice like here you have the point 1b, so here you have the point b1. Here you have the point negative 1, 1 over b, so here the point, it should be positive. Positive 1 over b, negative 1. Okay. So these are the general properties of exponential and logarithmic equations, and they're like useful to like know. Okay. So now that we discussed that, let's now let's like do some examples finding the domain of logs. That did not raise well at all. Anyway, so let's see. Suppose we have like f of x equals log, I don't know, say base 3 of x minus 4, right? And they want you to find the domain. So how would you do this? So remember that the domain for general log, so the domain for this is just x is greater than 0, right? So it's from like 0 to infinity. So essentially, x minus 4, we have to set that input greater than 0. So we have x minus 4 is greater than 0, and then you just solve this inequality. So then you get x is greater than 4. So interval notation, the domain is just 4 to infinity. Okay. All right, let's do another one. Let's say we have f of x equal to log base 2 of 5 minus 2x. Okay. So again, we have to set this whole thing to be greater than 0. And then solving the inequality, you get 2x is less than 5. Therefore, x is less than 5 over 2. And so then writing that in interval notation, you have negative infinity to 5 over 2. Okay? Alright. Now let's do some little bit more complicated ones. So suppose we had, so part C, suppose we had f of x is equal to natural log of x squared minus 9. Okay? So again, you're going to set x squared minus 9 to be greater than 0. And so you get x is greater than 9. So you get, actually, x squared is greater than 9. And so then from here, right, because like if you had, if you put negative 4 in for x, then you square that, that's greater than 9. But positive 4 squared is also greater than 9, right? So like the way I like to do it is like kind of just draw a number line. So if we were to draw like a number line right here, right? And we know that, okay, so we know that this is equal to 0 when x is equal to plus minus 3, right? So it's like the zeros. X equals plus minus 3. So then just like have negative 3 here and then 3 here, and then just test like each interval and see if it satisfies the original inequality. So this one. So like if you were to put negative 4 into here, like we already tested that, right? That works. Because you have negative 4 squared at 16 minus 9, that's greater than 0. So this works. Now if we test the number between negative 3 and 3, let's just say 0. We have 0 squared minus 9, so that's negative 9. Is that greater than 0? No, it's not. So this interval does not work. And then anything greater than 3, like 4. So 4 squared is 16 minus 9. That's also greater than 0. So this interval also works. Okay, and so then combining that all together, so you have from negative infinity to negative 3, and it's not included, right? Because it's strictly greater than. Like if it was greater than or equal to, then you could include it, but it's not. It's just strictly greater than. So it's negative infinity to negative 3 not included, and then union 3 not included, positive infinity. So this would be the domain for this function. Okay, all right, let's do last one. Suppose we have k of x, it's equal to log, and then we have absolute value x plus 1. Okay, so like always, set it greater to 0, and then let's see. Again, you're probably going to want to do like a number line for this one because there's like multiple values, or like multiple like different values that can satisfy this, so like it's not just one interval, right? So like the zeros of this is just when x is equal to negative 1. Okay. And actually, if you notice something, like absolute value of x plus 1, that's always going to be greater than or equal to 0, right? So honestly, you could take a little shortcut and just see when this is equal to 0. And that's when x is equal to negative 1, right? So that means that the only like x equals negative 1 doesn't work, because everything else is going to work because you have absolute value, and by definition, absolute value of anything is greater than or equal to 0. So essentially, the domain then is just negative infinity to negative 1 union negative 1 to infinity. So essentially, it's all real numbers except for negative 1, because at negative 1, it's equal to 0, whereas we want it to be strictly greater than 0. Okay? All right, yeah. So that's pretty much it for logarithmic functions. If you enjoyed this video and you found it helpful, please make sure to leave a like and make sure to subscribe as well. I'll see you guys in the next video.